Hi, and welcome to another video of Chem with Com. This is part two of Intermolecular Forces, States of Matter and Energy. This topic is going to be the last two, states of matter and energy. All right, so we talked a little about in the last video why things are different states of matter, and basically intermolecular forces can hold solids and liquids together so they can be solids and liquids, right? Without those forces holding them together, these atoms or molecules are all bouncing around, not getting stuck together, right? They're kind of like the glue that holds it all together, right? Energy can break these intermolecular forces. This is a little diagram of solid, liquid, and gas phases at their transition points. On the y-axis here, on this arrow here, is going to be energy. Sometimes we label it as big E, big capital E. All right, so let's track this here. Let's just do it for water because water is something common we use. We know the different phases. So yeah, we could start with solid water. That's the formula for water is H2O. All right, so let's say we start with water, solid water, and we increase the heat. So I imagine putting a pot on the stove with ice and you crank up the heat, you turn on the heat, and it starts moving to liquid, right? Meaning as you increase temperature, it's going to hit a certain point where it changes to liquid. Okay, cool. We're at liquid. We continue to heat it up, and then we hit some certain temperature or it absorbs a certain amount of energy, and then it now turns to gas phase. All right. So now let's take that, put it in the freezer. We were able to trap all the gas into a pot and a lid. Maybe it's sealed somehow. We're going to take that, put it back into put it into the freezer, right? As the temperature goes down, the energy is transferred away from the water and it now starts to condense into a liquid, right? This part here is liquid, right? So it's now liquid to liquid. It gets colder and colder and colder. It loses more and more energy. And then we hit a point where it's now solid, right? It's now frozen. Or sorry, this is, I believe, sorry, solid's supposed to be up here. So yeah, solid's right here. All right. All right. And you could also skip that too. There's conditions where if the pressure is a little different, depending on the pressure and the temperature, we can get a direct change from solid to gas, which is going to be what's called sublimation, and then back to solid. A straight shot without doing the liquid part is going to be deposition, right? So energy can break intermolecular forces or disrupt intermolecular forces. Pressure can also affect phase changes and physical states, right? Because they're related. So this is a generic, what's called phase diagram, right? We have this thing called a triple point. A triple point, oh, sorry, let's do the axes first. We have pressure on the y-axis, temperature on the x-axis. This isn't really a traditional graph where it's a dependent and independent variable, right? This just tells you, hey, at a certain temperature, at a certain pressure, it's going to be one of these three phases. You have solid, liquid, and gas. All right, this triple point is where solid, liquid, so I'm going to kind of fight the phases. L, lowercase s, this is G. Solid, liquid, gas all exist at once. Go to YouTube, Google, hey, triple point of something. And they'll have little experiments with a vacuum pump and maybe some temperature control, and they can manipulate it so that you can actually see solid, liquid, and gas appearing at the same time. Sometimes it looks like boiling ice, which is wild, like a big chunk of ice, but it starts boiling because, again, they're all existing at the same time. All right. So another feature of these phase diagrams are these transition points, right? This is the transition point between solid and liquid. So if you go to the right, it's melting. If you go to the left, it's freezing. Um, Here is vaporization. So vaporization is when a liquid turns into a gas. Condensation is where a gas turns into a liquid. Like the condensation on if you have a cold drink on a hot day, what happens is the molecules in the air turn back to liquid on your container, right? That has the ice in it. And then, like we talked about, you can go strictly from solid to gas without doing the liquid part at a certain pressure and temperature. And going from solid to gas is sublimation, and going from gas to solid is deposition. And these are all those phase change lines. Over here is a critical point. It's kind of where you get to something called a supercritical fluid, which is sort of like a gas and a liquid all happening at the same time, like both of those phases, right? Kind of cool, not as cool as the sublimation point. Um, or sorry, not as cool as the triple point because that you can see all three phases. All right. So again, this is a generic phase diagram. We're going to learn how to draw these or use these and whatnot. All right. So phase diagrams can help identify physical states of a substance. So let's say let's just write some numbers down. Let's say we have a kPa of, let's say 100. Right? That's kilopascals. We don't need to know much about gases till later, but this is the generic amount of pressure, just 100 kilopascals. At 100 kilopascals, and let's say we're starting at, let's say 300 degrees Celsius. So right here. So start point, 100 degrees Celsius. And 100 kPa, kilopascal. So 100 and sorry, 300 I said, right? 300. All right, so we're up here somewhere. That's going to start out as gas. Okay. So then let's cool it down. So let's say we have it fixed at 100 kilopascals. And let's say we start cooling it down. So start cooling down. What phase is next? What phase will it turn into? Into next, right? So we're cooling it down, cooling it down, cooling it down. Let me get a different pen so we could track this, but we're cooling it down, cooling it down, cooling it down. Boom. Once we hit something like 95, 98, something like that, we're going to turn into water. Or sorry, I didn't say what this was, right? Oh yeah, this is water, water. Right? So then where he went from gas to liquid. And we could say at about 98 degrees Celsius or so, right? A little bit below 100, we start turning into liquid. Now let's say we keep cooling down. Keep cooling down. What temperature does it turn solid? Right? So we're cooling, 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 boom. And we're staying at 100 kilopascals. So about here, that red line here is where it turns into, oh, sorry, redo that part, right? The red line where it turns into solid might be about 1 degree Celsius. Right? Because there's a little bit, and let's clear this up. Let's erase some of this stuff. Right? If we said the red line is at 100, which is right below there, right? And this is 0. It's a little crooked. Let me do that again just to make sure I'm not telling you the wrong number. And this is a little too close for my comfort here, but it looks like it's going to be close to 0. So let's just say about, I don't know, -1 to 0 degrees Celsius, right? That's when it'll turn solid. I'm not going to give you ever questions that close, right? We're going to give you kind of broader ranges. So it'll end up over here somewhere, right? So if you know the pressure and the temperature, you can locate the phase it's going to be on the phase diagrams. All right. Let's check this out. What phase changes can water undergo as the temperature changes if the pressure is held at 0.3 kilopascals? So here's about 0.3. We don't really know. All we know is that it's below zero point 0.6. And the relevance is that triple point ends up at zero point 0.6. So we want to be below zero point 0.6 at, let's say they're asking for 0.3. So what phases can we be? We can be solid or gas, right? Because if we track this line here, right, we hit the solid part and we also hit the water vapor part, right? We never hit the liquid part. So that's not going to be part of our calculations there. So solid and or gas, right? Solid and gas. Okay. What if it's held at 50? 50 is up here somewhere. We could just guess it's right here. So what phases could it be? It could be solid, liquid, or gas. All three, right? Those are all options. What happens is if you start changing the temperature, it could be ice. If you raise it, it could be water. Then you raise it again, it could be gas, right? So it all depends what the temperature at. But this is telling you we're keeping it at a fixed pressure, 50 kilopascals. All right. Another one. Identify the phase changes that carbon dioxide will undergo as its temperature is increased from -100 degrees while holding its pressure constant at 1500 kilopascals. 1500, I'm assuming it's something like around here somewhere. It's hard to tell because this is what's called a logarithmic scale. So this is here is more linear where it's like the numbers are kind of more by in scale. This you can see this is a 10 times the growth, 10 times the amount, 10 times the amount. 10, so 1500 I'm assuming is about right here, but it's hard to tell. All right, so as temperatures increase from -100, so we're starting here and looks like we can go to liquid and to gas. So we can be solid, liquid, or gas, all three of them. All right. At what approximate temperatures do these phase changes occur? So here, we're just going to take some guesses here. We're going to mark that and come straight down. And we could say that's something like, I don't know. So we could say solid to liquid is about -60 degrees Celsius. All right, let's do another one. This one here, just go straight down. This is -25. So we could say liquid to gas is about, let me see, -30 degrees Celsius. Right? And this is for carbon dioxide. Every substance will have its own phase diagram, and these are created experimentally. So you're not going to have to create any of these. You're just going to learn how to read them and check the temperature and the pressure and figure out what phase changes are there, or what phase it's in. Also, what phases it could be in if it changes pressure or temperature. All right. Heating and cooling curve. So let's take a look about, talk a little bit about this. All right. So this is um, another kind of graph or chart. And on here, this is more of a traditional XY chart where this is the amount of heat added. Oof, what is that? Heat is a quantity. It's a quantity of something. And here's temperature. What's the difference between heat and temperature, which is weird. So let's go through and just briefly describe it. We're going to look at some definitions. I'm going to explain it and we'll come back to this. All right. So here we're starting out as some, let's say we have something that's very cold, some ice. Let's say we have a bunch of ice in the freezer. We put it into a pot. We turn on the stove and we start heating things up. Right. So we're gonna raise the temperature a bit. Something weird happens here. We raise the temperature a bit here. Something weird happens here, and then we get into the gas phase. But let's take a look and figure out what the difference between temperature and heat is before we move any further, right? Temperature is a quantitative measure of hotness and coldness. It's just a direct reading. You usually use something like a thermometer, right? Heat is the transfer of energy between two things, right? It's a something you could follow. It's like it flows, right? If you have a blazing hot copper block and you put it in water, right? The heat from that copper block is going to flow or transfer energy into the water, right? Energy is the capacity to supply heat or do work. And this says intensive property, a property of a substance that is independent of the amount of substance. Joule is a SI unit of energy. And it has some funky definition, right? When a force of 1 Newton, well, we don't know what a Newton is, moves an object 1 meter. Well, we know what a meter is. And the units are kilogram per meter squared second squared, which again is weird. We also have an equivalence of joules and calories, right? Yeah. So specific heat capacity, intensive property of a substance that represents the quantity of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius or Kelvin. And we're going to do some math with that. So what I really want you to take away from this slide is heat and temperature. Two different things. Heat is something you could transfer. Temperature is just a measurement of hot, quote unquote, hot and cold, and we'll explain that next, right? So let's try to analyze what heat versus temperature. All right. Let's say I have a pool of boiling water. That's 100 degrees. Right. And then I have a tablespoon, or let's say I have 1 cup of water at 100 degrees. Right. And there's no more, we're not heating this up anymore. Maybe we heated it and then we stopped, right? The temperature is 100 degrees Celsius. Heat. Now let's talk about heat. Is there enough heat in this cup, right? Again, there's no more, we're not increasing the energy or the heat anymore. We just have a cup at 100 degrees and a pool full of water at 100 degrees, right? And let me just take apart that water thing, take off that water thing. So let's say they're both water. Now, drop an egg in. Egg. What's going to cook the egg? All right. The egg is going to be cooked in the pool because there's enough heat in there to finish cooking that egg. Whereas the cup only holds a certain amount of heat because it's a measurable quantity, right? Even though it's the same temperature, the pool full of water has more heat, right? Because it just has more of that water at that specific temperature, right? So that's the difference between heat and temperature. And we'll talk about that next. Let me actually just rearrange something on the fly, just so we can talk about it in the right order without hopping back and forth. All right. So another thing we're going to do is look at something called heat capacity. Heat capacity is the amount of heat something can hold on to, right? Or absorb, or yeah, hold on to. We have different things. One of the things with one of the substances with the highest heat capacity is water. There's helium. I didn't actually wasn't aware of that, right? I didn't know helium had such a high heat capacity. But water can hold 4.18, the specific heat is 4.18 joules per gram Celsius. Look at something with a lot less heat capacity. So let's look at gold. It's a very low heat capacity. So if I had 1 kilogram of gold and 1 kilogram of water, right? Water is going to hold much more heat, right? And it also means it loses that heat kind of slower, right? If you were to think about a piece of metal, let's say you had a kilogram of metal and a kilogram of water, and then metals can be any of these here, doesn't really matter. Sorry, that's not a metal. I'll put a star by the metals. Metal, metal. All right, they have fairly low heat capacities. What that means is, let's say you were camping or something, right? And you needed to warm up something to take into your tent with you to warm up the tent. So you heat up a kilogram of water and a kilogram of, let's say, lead. It's probably not safe, but let's say heat up a kilogram of lead, right? And you bring it into the tent. Lead can only hold a small amount of heat. So it's going to release that heat and then it's done. Your tent's going to be cold in a few hours, right? Or very few minutes, actually. Here, water can hold a lot more heat. So water will continually release that heat or transfer that energy to the surrounding air in your tent, keeping you warmer longer because the heat capacity is higher, right? It has a higher heat capacity. We're going to measure this heat capacity in a few slides, but we're going to look at this and this Q is heat, or yeah, Q is heat. C is what's called specific heat or heat capacity, right? And that's listed here. These are all the heat capacities, and the units are for this one is joules over grams Celsius, right? You might remember this from some of the quiz zero stuff that we did, the review quiz. But yeah, the mass of the substance, that's little m. It shouldn't be actually italicized. It should just be mass. For this equation, it is italicized, I think just because of the program. T is temperature change. It's the final temperature minus the initial temperature, right? So we're looking at changes in temperature because heat's moving around. So obviously the temperature is going to change. So we're looking at the final temperature minus the initial temperature. We'll come back to this equation in a few, but we just basically get the specific heat here. They have to tell us what the mass is or what the temperatures are, and we can plug that into this equation. And again, we'll do that in a few slides. All right. So let's go back to this heating and cooling curve because now we know the difference between temperature and heat. All right. So again, we took a bunch of ice from the freezer that's at negative 10 degrees. We put it on the stove, turn on the heat. And what we're doing is now we're increasing the heat added to the thing. So here it's just solid water heating up. So ice is absorb ab, absorbing heat. All right. And as it's absorbing heat, temperature is increasing. Actually, let me write this a little easier to read. All right. So as for this part here, as Q as heat goes up, we're going to say temperature goes up. That kind of makes sense, right? To me, that makes sense. As you increase the heat, the temperature is going to go up. What's going to happen is you have really, really cold ice, and then you're going to have slightly warmer ice as it keeps adding heat, right? As the temperature goes up as well. So what to me is weird is here is weird, right? This is a phase change. This is where your solid ice, it has absorbed so much heat, the heat is now going to be used to break those intermolecular forces. So phase change and then breaking of intermolecular forces. Let me spell it out one time. Intermolecular forces, right? So boom. Okay, cool. So we used, because right here, it's what's happening is the heat is going up, but the temperature is the same. All right, let me just write same. All right, so that's the weird part. This one I understand, right? Heat, you add heat, temperature goes up. Here, when you add heat, it stops. All the energy that the heat's contributing to that substance is now breaking those intermolecular forces, specifically for water, hydrogen bonds. All right, so now let's figure out what's going on here. So once we turn into liquid, the liquid is just going to continually heat up. It starts at 0 degree water, liquid water, and then it goes all the way up to 100 degree liquid water. But as soon as it hits 100 degrees, we have that weird phase again, right? We're going to say phase change, and that's where the heat goes up, but the temperature is the same. Because the energy we're putting into this now liquid water, instead of it heating up anymore, it's at max capacity. It's going to start breaking those intermolecular forces. So let's say water looks something like this. Hydrogen bond, HOH, right? The energy, we'll say heat at 100 degrees Celsius, right? At 100 degrees Celsius, that heat now is going to start breaking those intermolecular forces and causing that to go from liquid to gas. Now, here is the last part. We are just in the gas phase. And as you can see, oh, sorry, I forgot to do this. Here, as heat goes up, temperature goes up, and gas phase also, once it's vapor, as heat goes up, temperature goes up, right? So then again, those are the easier ones to figure out. To me, it's hard at this point to figure out, hey, we're actually changing phases, right? All right. Okay. We'll talk about a couple other terms. Exothermic processes mean when you do a chemical reaction, heat's released. So explosions, burning wood, there's Let's see, oxyacetylene torch. That's just combustion, right? There's a something called a not ferrite. It's a I forgot the name. But it's a very, very exothermic process. They use it to actually weld train rails like on the spot. Can't remember. I can't believe I can't remember that. All right. And then endothermic reactions mean the reactions turn cold, right? So they have these cold instant ice packs. You break them. What happens is you have ammonium nitrate and water, and when you mix the two, the temperature drops, right? So you have an endothermic reaction, which means it gets colder. Exothermic means it gets hotter, right? Okay, let's now use this equation and try it out. So they're asking how much heat in joules must be added to a 502-gram iron skillet to increase its temperature from 25 to 250 degrees Celsius. So the specific heat of iron is this. So we're just going to use these numbers and identify these different variables, right? So let's try it out. So Q is what we're trying to find. How much heat in joules? That's our question. Now, we have a 502-gram iron skillet. So that's, I'm going to write these in order, and then we'll go back and initial. So I have the Q is heat, C is heat capacity or specific heat, M is mass, T final is the final temperature, whatever it ends up at. T initial is whatever it starts as, right? So C is heat capacity. It tells us it's 0.449 joules over grams times Celsius. Mass is 502 grams. Temperature final is 250 degrees Celsius. Temperature initial is 25 degrees Celsius. All right, let's set this equation up. Q equals C, which is 0.449 joules per gram Celsius times 502 grams times temperature final, 250 degrees Celsius, minus temperature initial. All right, I'm going to do stuff. Remember PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. So let's do this one first. I'm just going to transfer these numbers over so we don't get lost. Grams Celsius times 502 grams. 250 minus 25 is going to be 225 degrees Celsius. Let's start canceling stuff out. Since we have a Celsius up here and a Celsius here, those cancel out. And since we have a grams here and a grams here, those cancel out. So all we're left with is joules now. So our heat, which is perfect because that's what we're looking for. Let's look for a online calculator. Let's see here. Do we have one here? Let's see. Online scientific calculator free. Let's check out this one. We'll use a different one for the next one. All right, so it's going to be 0.449 times, I think it was 502 grams times now 225, and there's no units because those all canceled. Actually, the grams already canceled out too. So this is the number we have here. 50714. 50714. 50714.55. Ooh, so now we're going to have to do sig figs. So let's look at the sig figs. We should have done this earlier, but here. When you subtract, we use the least amount of decimals. They're both 0 decimals, so 0 decimals here. This is great, right? So these are all significant. So because these are all multiplied, we have 3 sig figs here, 3 sig figs here, 3 sig figs here. Our answer should be 3 sig figs. So I'm going to put 3 sig figs here. Our answer is going to be 507. We can't say 507 because 507 is drastically different than 50,714, right? So we have to add a couple extra digits, but this is still 3 sig figs. So that's going to be our answer. And that's all going to be in joules. Now, since we know the metric system already and prefixes and everything, we could also call this 50.7 kilojoules, right? And if you need a refresher, go back to topic 6. It walks us through the exponential notation, scientific notation, standard notation, and going back and prefixes, right? So we could also say this is 50.7 times 10 to the third joules, right? These are all the same answer. It's all the same value. It just looks different, right? This one has it in joules. This one has it in kilojoules. This one has it in joules, but it has that exponential notation, right? So, all right, let's continue. Another one. A piece of unknown metal weighs 217 grams. When the metal absorbs 1.43 kilojoules of heat, its temperature increases from 24.5 to 39.1. Determine the specific heat of this metal and predict its identity. So let's check that out. Let's do it over here. We can do a little smaller. Q, C, M, temperature. TF is temperature final. This is temperature I, temperature initial. All right. Q, they told us it was 1.43 kilojoules. C is what we're trying to figure out. We're trying to measure the specific heat. Mass is 217 grams. Temperature final is 39.1 degrees C, 24.5 degrees C for the initial temperature. Let's work this out. We're going to put I'm going to write the whole equation and plug the variables in. C times M times TF minus TI. All right, let's plug it in. Q equals, we don't know. Oh, sorry. We know Q. It's 1.43 kilojoules. All right. We have specific heat. Mass is 217 grams times 39.1 degrees Celsius minus 24.5 degrees Celsius. We're going to do parentheses first. So let's do, let's see, where's this guy? All right, 39.1 minus 24.5. All right, we got 14.6. Let's do sig figs. We have 1 decimal here. Here we have 1 decimal. So the answer is going to be, I already lost the answer, 14.6 degrees Celsius. Already has 1 decimal, so we're good. All right. We'll just say 1 decimal to keep track. All right. So then we have Celsius, 217 grams equals 1.43 kilojoules. All right. We want to isolate heat capacity by itself. In order to do that, we have to move everything here to the other side of the equation. And what we're doing here is called isolating a variable. To isolate the variable, we're going to do the opposite operation of what's being done to it now. So if you have, this is the operation, this is the opposite. Should probably come up with a different word, right? So if it's plus, it's minus. If it's minus, the opposite is plus. If it's multiplication, the opposite is division. If it's division, opposite is multiplication. Well, here we see that multiplication sign. So we have to divide it. I'll do it in a different color to keep track, right? 217 grams. So here we do 217 grams. Here we have to do divide by 14.6 degrees Celsius. Divide by 14.6 degrees Celsius. Well, if you look here, these cancel out and these cancel out. Here we see 1.43 kilojoules over 217 grams times 14.6 degrees Celsius. So let's do this in the calculator and we'll move it down here. And we have to keep track of those units. So let's do it here. Let's clear this. 1.43 divided by, I think it was, 217. Let me clear this and I'll show you what you need to do. So you want to put this in parentheses, 217 times 14.6. Closed parentheses. All right, so that's what it looks like, right? So we enter, it's 4.5136. So this says it's going to be 4.5136 times 10 to the negative fourth. And let's do units now. Kilojoules, because we still have the kilojoules. We have grams and we have Celsius. Over grams Celsius equals the heat capacity. And we don't know what metal it is, right? We have no idea what this is, right? But the units for this is in joules per gram Celsius. So we need to go from kilojoules per gram Celsius to joules per gram Celsius. And we know how to do that. Let's try it. We know the conversion rate of kilo to Celsius, kilo to regular joules, kilojoules to regular joules is 1,000. We know there are 1,000 joules over 1 kilojoule, right? Because kilo means 1,000. These cancel out. Oops, I never wrote this number. We're going to do 4.5136 times 10 to the negative 4. All right, so the kilojoules cancel out, so we're just converting this one. So the units are going to be joules per gram Celsius. And we have 3 sig figs, 3 sig figs, 3 sig figs. So our answer right here is going to be 3 sig figs. Let's try that out. So basically it's 4.5136 times 10 to the negative fourth times, oops, let's back that up, times 1,000, which is now going to be 0.45136. 0.45136 4, 5, 3. Because that's going to be 3 sigmas. All right, so we're like, what could this substance be? Well, the closest is iron. We can say possibly iron, right? That's going to be the substance, right? So again, we looked at the variables, we plugged them in, we did the parentheses first, and then we needed to isolate the variable by performing the opposite operation to both sides of the equation to get everything on one side. Then we had to convert from kilojoules per gram Celsius to joules per gram Celsius, because that's what these units are, right? Joules per gram Celsius. And just to show you, right? Joules per gram Celsius. Let me just erase that. So, right? Joules per gram. That's why we needed to change, because we needed to get that joules instead of kilojoules. All right, well, that's it. If you have questions, let me know in class, and I'll catch you later. I always forget how to do this. All right, I'll see y'all later.